The history of civilization is the story of man's tireless, never-ending search, that which is always beyond his grasp.
Where's my new golf ball?
From the very dawn of time, man has tried to extend the range of his vision, to pierce the unknown, to learn what lies ahead. The caveman, exploring his mysterious world with the aid of a torch. A hardy pioneer pushing westward through the wilderness, scanning the distant horizon. The sailor, perched aloft in his crow's nest, constantly alert to the dangers of the sea that lie ahead. So man moved forward through the ages, reaching out toward new goals, ever probing, ever seeking, ever searching.
I paid $2 for that golf ball.
With the coming of the scientific era, man's ability to increase his range of vision grew by leaps and bounds. Every day brought new inventions, new devices, all helping him to see better and farther than ever before.
I'll find it if it takes all night.
In the field of aviation, perhaps more than any other, the need to probe what lies ahead is most pronounced. Pilots in the early days had to depend solely on their own eyesight to bring them safely to their destinations. But as instruments were developed, their range of vision was steadily increased. The gyro compass, operating independently of the Earth's magnetic field. Two-way radio, supplying direct contact between air and ground. The artificial gyro horizon, telling the pilot when his plane is horizontal under blind flying conditions. Voice radio communication, automatic direction finding equipment, enabling a plane to home to any audible signal. High-frequency navigational systems. And now, at last, comes the newest and greatest addition to this impressive list. Radar.
Radar?
Why, yes.
Well, that's a new one on me. I thought radar was strictly military stuff, you know, for bombers and battleships.
It was originally, but now Pan American is installing radar in its passenger planes.
No kidding. I bet it's pretty complicated stuff, huh?
Not really. You see, the whole thing is based on the echo principle.
Echo?
Yes. Suppose you were on a mountaintop and... Oh, wait, I have a better idea. Let's put you on a mountaintop. Now, would you mind shouting something?
Okay. 4!
Good. Now let's see what happened. The sound waves of your voice traveled out in all directions. Part of these sound waves hit the mountain and were reflected back, just as light waves are reflected by a mirror. Now, suppose we wanted to measure this distance. We know that sound waves travel at about 1,000 feet per second. So, let's ring a bell and count the seconds until the echo returns. 6 seconds, which means that the sound waves traveled a total of 6,000 feet out and back. Well, the principle of radar is exactly the same, but instead of using sound waves, we use radio waves, high-frequency ones called microwaves. Knowing their speed, we can measure distances just as we did with your echo.
Well, do radio waves go fast?
Very fast. They travel at 162,000 nautical miles per second. In other words, in the space of a single second, a radio wave could go 7 times around the world.
That's traveling. This radar stuff must take plenty of fancy equipment.
You bet it does. Airline radar sets consist of 5 very intricate parts. The transmitter receiver, the antenna, the synchronizer, the plan position indicator, or scope, and of course, the control panel. The antenna, located in the nose of our plane, is covered by a fiberglass shell called the radome. This shell is transparent to our radar beam. The scope contains a tube like that used in television sets and acts as a screen on which we see our radar picture. Standard installation provides two scopes, one for the pilot and one for the co-pilot.
Okay, so how does it work?
Well, let's look at our parts in diagram form. The synchronizer generates timing impulses called trigger pulses at the rate of 400 a second. These are sent to the transmitter and the scope, both at the same moment. The transmitter, in turn, sends a short pulse of radio energy to the antenna. This pulse travels from the antenna along a narrow beam. At microwave speed, the round trip to an object 150 miles away takes less than 1/500th of a single second. Now let's get back to our scope. The scope translates this pulse into electrons, which cause a small luminous spot to appear. Each new pulse is deflected, so that a steady flow of them keeps moving to the edge of our screen. Actually, they move so fast that they create the impression of a single, almost invisible line, which is called the sweep. Now, let's look at our radar antenna. See that reflector? It's a giant addition of those found in flashlights, and it's used for the same purpose, to concentrate our beam. This makes the beam pretty narrow, so in order to get the greatest coverage, our antenna turns slowly in a 360-degree circle. The sweep on our picture is coordinated with this, so that both beams move together.
What's that dark wedge at the bottom?
That's the shadow cast by our airplane itself.
Well, what happens when the beam picks something up?
When something appears in our beam, the microwaves are reflected back to the antenna, then to the receiver, and finally to our scope. The radar beam and the sweep are so matched that an object picked up by the beam appears in an exact relative position on the scope. Remember that our sweep line is continually revolving in time with the beam. As it passes over the face of the scope, it literally paints a picture for the pilot to study. Our sweep is set so that the aircraft heading is always at the top of the screen. Now, we add a grid for bearings and some range circles to help in measuring distances, and our story is complete.
Well, gee, this is all pretty interesting, but what's the point? I mean, how much good does it do the pilot of a passenger plane? Does radar really help him much?
It helps everybody. By giving the pilot eyes that can pierce fog, haze, smoke, and clouds, radar helps him get you to your destination quickly and safely, with greater efficiency, greater saving of time, greater passenger comfort. It helps the pilot to know his terrain, thereby lessening his fatigue and that of his crew. It helps warn him of approaching storms so that he can steer clear of them and give you a smoother, more enjoyable ride, or find a pathway through them, saving detours that might cause loss of time.
What was that you said before about helping the pilot to know his terrain?
Well, terrain mapping is one of the main functions of airline radar. It's possible to tilt the radar beam up and down, which helps to give the pilot a clear idea of the ground ahead of him, regardless of the visibility conditions through which he's flying. Let's look at some actual radar pictures made during a Pan American Airways flight to Panama. We're approaching San Blas Point, flying over a solid layer of clouds. Direct vision isn't much help, but the first sign of land appeared on our radar scope about 100 miles out. Here we see San Blas on the 50-mile range setting. 24 miles out, and San Blas Point is clearly visible. 2 minutes later, we switch to a shorter range for a more accurate distance check. San Blas Point is now 16 miles ahead, and we're right on course.
Hey, the water showed up black and the land white. How come?
There's a very simple reason. Smooth surfaces, like bodies of water, cause our beam to bounce off, to be deflected, so it fails to return to the antenna, and those areas appear dark on our screen. Land surfaces, though, have irregularities, some small, some large, but usually enough to reflect the beam back to its source. As a result, these pulses register on our scope, and land masses show up bright. When approaching a mountain, our radar beam will bounce back from the near side, showing brightly on our screen. The far side of the mountain, which can't be reached by the beam, remains in shadow. So a radar echo of a mountain peak would look like this. Now let's take a look at the most important use of radar, its ability to map weather conditions. Our pilots try constantly to give you the smoothest and most comfortable ride they can, but a lot depends on the weather. Now, thanks to radar, the pilots can see storms long before they reach them and avoid them wherever possible. This means more comfort for our passengers and a smoother ride than ever before.
What do you mean, see storms? I thought you said radar cut right through clouds.
Through ordinary cloud cover, yes. But areas with heavy rainfall, cold fronts, thunderstorms, these show up very clearly on the radar scope. Like this. And this. And this. Even hurricanes show up on our screen. Here's a recent one off Cedar Keys.
I'd sure like to steer clear of that.
So do we. And radar makes it easy. Now let's look at one more device called Contour. This helps the pilot probe the center of a thunderstorm as well as its outer edges. Contour reverses the brightness of the echo so that the worst part of a storm shows up as a dark mass inside it, like this and this. Result, the pilot can not only see storms miles away, but he can see into them.
Gee, I get what you mean now about radar being helpful.
Let's listen to some actual comments by Pan American pilots taken from their reports.
Invaluable. Use of this equipment provides extra reassurance to the crew, lessens the possibility of fatigue.
Radar helped us avoid several storm areas. Stewardess served all meals right on schedule. No difficulties whatsoever.
I believe radar is almost indispensable on the Lisbon-Joburg route. Makes for tremendous saving in time and a more comfortable flight.
Terrific help in making a landfall approaching Gander westbound.
Radar is wonderful. Our flight was conducted with slight detours. Passengers enjoyed normal flying conditions and service, whereas other flights in the area were getting plenty of turbulence.
Say, you think maybe I can see radar in action?
Sure thing. Climb aboard. Pan American is always happy to have its passengers visit the cockpit, under supervision, of course.
Uh-oh, fog. I can't see a thing.
No, not with the naked eye, but let's take a look at the radar.
Hey, we're over the golf course.
I will head out to sea. If you watch, you'll catch the coastline.
Yeah, there it is. Clear as a bell. Just like a map.
Now, let's raise our beam and see what the weather's like up ahead.
There's one of those thunderstorms.
That's right. According to our range markings, it's about 30 miles away. We can move slightly to the south and avoid it easily.
Hey, this is really something. Never thought I'd be playing tag with the weather. Uh-oh. What's that we're coming to?
It's a solid squall line, stretching for miles.
Things are going to get bumpy. We'll have to go around it, huh? Make a detour?
Nope. Take a look at what our radar shows. The storm appears to be solid, but you can see that there are actually only 3 heavy echoes. That leaves plenty of clear space in between for us to fly through. Well, that was pretty simple, wasn't it? Saved us a lot of time, too.
And not a single bump. From now on, it's going to be more fun to fly than ever.
Now, let's head back to your golf course.
You enjoy your trip?
I sure did. I learned things, too. It really is my golf ball!
Wait a minute. Radar isn't quite that good. At least, not yet.